Okay, welcome back to day 2. Last class we ran over and I still had some content to discuss, so I threw it up on the board here real quick. This is all, it should hopefully all be mostly recap, but again I like to start the class basically redoing everything, assuming you know nothing, but if you don't know anything about thermodynamics it might be like drinking from a fire hose. But hopefully this is a recap. So we spent Monday talking mostly about the history of the first law and its formulation. It's been known for quite some time that mass is conserved, except in nuclear reactions, which they didn't know about back then. Energy is conserved, but sort of the tricky part of all of that was keeping track of all the different forms of energy and then realizing that every individual form of energy was actually just energy. So the internal energy that's stored by matter, the kinetic energy stored by velocity of particles or objects, some form of potential energy. We just use this giant, I think that's a giant phi? Psi? One of those big Greek letters. This could be electrical potential energy. It could be gravitational potential energy. Any of the number of different ways you could store energy. And in fact, you could almost kind of invent your own form of energy to simplify the mathematics if you'd really like to. So when we do the first law of thermodynamics, and this is the common form of the first law that you'll just see kind of thrown out at the start of thermo textbooks. So what we're looking at here is d dt, right? So this is the differential rate of change as a function of time. So in this case, we write little t for time, big T for temperature. We are keeping track of the internal energy. We're keeping track of the kinetic energy, mass times velocity squared over 2, 1/2 mv squared, and the potential energy. So in the case of gravitational potential energy, it's, so if we call it gravitational potential energy, I'll just say GPE, I suppose. This would be equal to m rho g h. I think that's the right units. Rho g h, maybe just,
Is that n for mass?
the mass is there, let's see, kilograms per cubic meter, so no, that we wouldn't have the density in there, it would be something slightly different. So that we would get rid of this. Normally gravitational potential energy is rho gh, which is equal to mass over volume gh. So if you pulled out the mass, this term here for gravitational potential energy would simply be gh over the density. No, I'm sorry. We wouldn't have the specific. It would just be the total volume of the system. Yes, I think that's right. But regardless, we're not going to consider these terms anyway, for the most part. So this right here, this keeps track of the total energy of the entire system, which would basically be anything that we would like to draw a box around. So this term right here, there is no enthalpy in this term, right? We'll talk about why that's the case. We're just keeping track of the total energy. The U tells us everything we need to know about, we know now, the molecular rotations, vibrations, translations of the gas particles or the liquid or the solid particles. That's what that U term represents. The mass and the velocity, that's basically if you have this thing on a big rope and you're swinging it around in a circle, for example. And then gravitational potential energy or electrical potential energy, if we just raise this up and put it on top of something. I guess that's a form of energy that we have it stored in. Now on the right-hand side, we're keeping track of all of the things that are going in and out of the system. So we're putting a little dot on top of everything, whereas the dot over something x is going to be equal to 1 over time. So it's a flow rate term. So the mass dot would be the mass flowing in as a function of time. The q dot is the energy flowing in the form of heat as a function of time. And the w dot would be the work flowing into the system as a function of time, or power terms. Now on the right-hand side, we have the enthalpy, and I'll talk about that next. We have the velocity of the particles of every stream. We're summing this up over all the streams k. So we have 1, 2, 3 going in, 1, 2, 3 going out. All we are doing is being accountants. energy accountants. We're making sure that we do not violate the law of conservation of energy. That is 100% just what this expression is here. So if you have a different velocity of particles going in as going out, technically you'll be getting more energy in as out if they're coming in faster and leaving out slower. Same thing here with potential energy. If these pipes are towards the ground, these pipes are towards the top, technically it takes energy to raise that fluid up. All of these are different forms of energy. For chemical engineering thermodynamics, these terms are basically going to be zero. Because the enthalpy or the internal energy is generally going to be much, much greater than those terms in general. Now, there's some questions that we'll have that'll consider, if I have a bouncy ball and I drop it from this height, by the time it bounces and settles, how much warmer would it be? Right? So we may have questions like that on an exam or a homework, but in that case, I'll remind you how to calculate gravitational potential energy. But the key thing to remember is that energy is conserved. So I'm taking a particle, I'm raising it up, I'm giving it energy, I'm letting go of it. Eventually, it might bounce up and down, up and down, up and down, but eventually it'll settle. So I will have given it energy and then returned it by letting it drop. It'll bounce, that'll dissipate some of the energy, and it will heat up a little bit. And if we did that exercise, you would find out it heats up a very, 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 very small amount. So it's not a big deal. With heat, you can have multiple heat in streams, multiple heat out streams. With the work, we have two different forms of work. One is going to be the shaft work. This would be from an impeller or a blade or a turbine, somehow where you're just kind of extracting work or giving work into the system. So if you had a pump in this process and that blade was spinning, that would be giving the system energy. Or if you had a turbine expander, you would be expanding the gas in a particular creative way to extract work out of it. This last term here, P dV dt, PV, what are the units of P times V? It's work. Right, so for the gas constant, I always remember 8.314 joules per mole Kelvin, which is equal to meters cubed Pascal per mole Kelvin. And this is the only value of the gas constant that I ever remember. I don't know any of the other ones. So when you have the system expanding, you have a negative sign here. Because as the system expands, it has to push on the surroundings at a certain pressure. The more it expands, the more work it has to exert on the surroundings. Likewise, if you compress something, you're giving energy to it. And this is one of the ways that Joule developed relationships between PV work, kinetic energy, electrical energy, and internal energy. And that's where he really solidified the first law of thermodynamics. Right, so this is the classic form of the energy balance that we will start off with in this class. But we won't be spending a tremendous amount of time on energy balances because we're going to try and quickly transition to, there we go, marker on my shirt. We're going to quickly transition to phase equilibrium problems. Okay, now enthalpy. Enthalpy is a made-up term that is useful. So how enthalpy works and why we keep track of it. If I have a system here, and I have a pipe coming in and a pipe coming out, who knows what's going on in the system? In order for me to force the fluid physically into the system, I have to do work on the system. That fluid doesn't want to spontaneously flow. So what's going to happen is I have a pressure that's going to push a volume element of fluid into the system. That work going into the system there is PV times the mass. I have this little V hat, which corresponds to the density, it's the inverse of density, but meters cubed per kilogram. And in the past, I've also written V underbar, which is meters cubed per mole. This is the notation following the Sandler book, which is very meticulous. I don't expect you necessarily to adhere to the hat being per mass and the underbar being per mole. Just note that whenever you do your own work, if you're making it specific volume, just give it some sort of a hat or a squiggle or something. This notation is going to change from source to source. And I'll try to be consistent with the hats being for mass and the underbars being for moles, but I may slip up from time to time. So this term right here will be units of energy going into the system. Right? PV is energy, but we're dividing by kilograms and then timesing by kilograms. So this all works out to be energy. So I have to physically somehow force that volume element of fluid into the system, and then when it leaves, the system is then pushing out another volume element going out of the system, which is what we have here. Now if we substitute that into basically this expression here, where we have a series of mass flow rate streams all undergoing the same process, this volume element of fluid has internal energy, the U. It has this additional PV work to actually physically force it into the system. And then it also has its velocity and potential energy. We simplify that by just writing it as the enthalpy H. So here we go. So enthalpy is just 100% a made-up function because it is useful, and that's it. Okay, so that basically wraps up the first law of thermodynamics. Now, the key part about applying this formula here is we need to talk more about how we actually calculate these enthalpy values and how we calculate the internal energy. And that's where we'll be spending more of the time. But the energy balance component of thermo is relatively straightforward. All you're doing is keeping track of all the sources of energy in and out. So I'm confident that if every one of you had a steam table in front of them with the properties of water, and I said that the water enters at this temperature and pressure and it leaves at this temperature and pressure, I feel confident that you could apply this formula here to solve for Q or W or whatever the case is. That's not the difficult part. The difficult part in thermodynamics is we don't want to have to use a steam table, because a steam table means that I had to go into the lab and measure the properties of water at every conceivable temperature and pressure. So I wouldn't have to have thermodynamics if I just had an infinitely large lab with an infinite number of people working in it and measuring all these properties. So the whole point of what we're trying to talk about is how do we actually predict and calculate what H is, what G is, what A is, what S is. Then we don't have to rely on laboratory experiments. We can just predict it from some base level of properties. So what we're trying to do from all of this class is just be convenient and lazy. And so the formulation of thermo is more or less to reduce the number of properties that I have to measure in the laboratory to tell me everything I need to know about the system. And through that, it's a lot of tricky math. And a lot of it's arbitrary, but it's arbitrary in a very specific and useful way. Right? Over years and decades and centuries, people have tried new formulations and worked it out, and what we're going to be teaching is the easiest, so to say. Okay, that wraps up intro to first law. So now we're going to talk about the history of the second law. Okay. The first formulation of the second law of thermodynamics was by Clausius. I didn't write down his first name, but I have the year. 1854. I'll paraphrase what his definition was, but essentially, if we have two bodies, one that is hot, one that is cold, where we say that the hot reservoir is at a higher temperature than the cold reservoir, basically saying that this is not possible.
A transfer of heat from cold body to hot body, right?
Bingo. Heat can't go from hot to cold. So sorry, cold to hot. Cold to hot. There's a problem with this definition. In order to define the second law, we have had to know what temperature is. We had to define what hot is, we had to define what cold is. So the issue here is that from fundamental thermodynamics, temperature is actually a derived quantity of entropy. So this law here, while it is true, it doesn't actually really fundamentally capture the essence of the second law because it relies on definitions that rely on the second law. So it's a big cyclic logic problem. And I will say to this day, people are still coming up with new ways to explain the second law of thermodynamics. In 1999, there was this massive paper that came out that I taught the very first time I taught this class, and it wasn't particularly useful. But some mathematicians and physicists are trying to better define the key properties of entropy in order to come up with a more elegant formal version of the second law. The Cliff Notes is basically no one can really describe it very well, but we'll get to that in a moment. So this is our first attempt at defining the second law. The next iteration, I guess this one is a little bit earlier. Kelvin in 1851 and Max Planck in 1897. They had their other sort of a definition that they used. So if you have a hot reservoir, we have some process. This could be very simple, this could be very elaborate, this could be a massive system, it could be extremely intricate, or it could be a small little widget. And this definition, I'll paraphrase again, more or less says that no process is possible, the sole result of which you remove heat from a reservoir and perform work. So you can't cool something and only get work out. So effectively, if we were able to do this, we could extract work from anything in the world, right? We could take a hot cup of coffee and extract all of the energy from it, getting it back to room temperature and turning it into work. So this is not possible. And then we get into the more abstract definitions of the second law of thermodynamics. An individual named Theodori. Don't remember where he's from. Unfortunately, I should have looked that one up. 1909. Now, this one here, I'll read it out. This is credited as sort of the first fundamental mathematical description of the second law. So they say it's the first self-evident mathematical foundation of thermodynamics. So the principle of Cassiodori states that in any neighborhood of any state, there are states that cannot be reached by an adiabatic process. So basically what it means is that some things just don't happen spontaneously. So it's a very mathematical, fancy way to more or less say that and I understand that this is a very unsatisfying definition of the second law of thermodynamics. Basically, it just says there's something that's called entropy, it has a value, and you just can't magically go from one state of entropy to something that has a higher state of, you can't spontaneously go to a state with lower entropy. There we go, that'd be backwards. So one thing to clarify, state. What do I mean by state? Anyone want to take a stab at it? What is a state?
I think of like the temperature, pressure, conditions.
Mm-hmm. State is a fancy term to classify all of the properties that we may care about a particular system. It could be its location, it could be its temperature, it could be its pressure, it could be its thermal conductivity, it could be its phase. Well, probably not thermal conductivity, that's a property. So when we say state, thermomath is nice and convenient. So when we say we're going from state 1 to state 2, and we're integrating, let's say, du, for example, what that means is that state 1 contains pressure, the temperature, the density, the enthalpy, the entropy, whatever we care about. The state is the collection of all of the properties of the system that we care about. When we go to state 2, it's basically the same thing, but it's the second pressure, the second temperature, the second specific volume, and so on and so forth. So when we have an expression like this, where we're going from state 1 to state 2, sometimes we can just say, oh, okay, sure, that's delta U, great job, there we go. Going from state 1 to state 2. But when we actually have to calculate the delta U going from state 1 to state 2, oftentimes we'll break it up into several different steps. So we'll say we'll integrate from 1 to 1a du plus 1a to 1b du plus 1b to state 2 du. And this would be, maybe I took a path of constant entropy, right? So I'll say that ds is equal to 0 for this step, meaning I'm following along an isentropic path. This would be something that would be for a reversible process, like an isentropic expansion. Then maybe on this step, I'll say that dt is equal to 0, isothermal process. And then let's say this step here, I'll say that dp is equal to 0. I'll say this is an isobaric process. So when we go from state 1 to state 2, we're going to break it up into individual smaller steps that kind of help us use sort of a plug-and-play or grab box style of math, where we're going to learn how to do this calculation, then we're going to learn how to do this calculation, then we're going to learn how to do this calculation. And the reason why all of this works is because S, U, G, T, P, all of these different functions here, they're all state functions. Now that term rings a bell? Meaning it doesn't matter how we got to a temperature of 300. A temperature of 300 is a temperature of 300. Doesn't matter.
Only conditions from the start and at the end.
Exactly. So we don't care how we get to 300, we just know we've gotten to 300. Entropy is a state function. Internal energy is a state function. Gibbs free energy is a state function. So even though the process may take some sort of arbitrarily complex pathway, we can break it down into individual steps. The next thing to mention, just to clarify so we're all starting off on the same page here. When I write ds, for example, would be the rate of change of entropy with respect to anything. So if I have an expression here, ds is equal to, let's see, I don't want to mess this up off the top of my head. But basically, we can just write this over anything. We could say it's a function of time. We could say ds as a function of internal energy, ds as a function of temperature. Right, so when we write ds, we're basically saying, when you change anything, this relationship still holds true. So that's why we don't bother with writing a full total differential here, because you can just use the same equation for anything. You can use it as a function of time, temperature, pressure, internal energy, concentration. You can use it as a function of anything. So when we write ds, it's just a shorthand way to simplify things. When we refer to state, it's a shorthand way to simplify. We don't care what are the original properties of the system. This law holds true no matter what. Doesn't matter if you start off at infinite temperature or 0 temperature, this law is going to hold true. Doesn't matter if you change the time, doesn't matter if you change the internal energy, doesn't matter if you change the temperature, doesn't matter if you change the pressure, this law holds true. So these are some shorthand ways that we can save time in our mathematics of derivation. But they are potentially a little bit tricky when you see it for the first time. Good. So hopefully I'm not skipping over any of the tricky definitions here. Okay. History of the second law, much less fun and descriptive than the history of the first law. And that is because we are still more or less trying to figure out the best way to quantify and define it. I believe the saying is credited to Einstein that the second law of thermodynamics is the most perfect law in all of physics, because it is simple and has never been disproven. It is literally just ds is greater than or equal to 0. No other equation that you'll encounter is quite so easy to write down, but still quite so frustrating. Okay. All right. So, what you typically see in an undergraduate class for the entropy is ds dt is equal to q dot over t plus s dot gen. Does this look familiar? Where does this come from? So we're going to do a quick little derivation using what we've learned yesterday and today to kind of generate this equation so that we can start to use it and apply it. So I have some system that's contained within an infinite bath. Right, and this bath is the entire galaxy, more or less. And it's going to have a constant temperature. The system has temperature, volume, which we're going to say is constant. The reason why we say volume is constant is so that there's not going to be any PV expansion work. So there's no energy going to be transferred into this system by compressing it or by shaft work or anything like that. So the only way that energy can transfer into this process is by heat diffusion. And it's going to have its internal energy. So if we write the first law, the overall energy of the universe, in this case. So we write du is equal to what? What is the overall energy of the universe? The overall rate of change of energy in the universe. Zero. Yeah, it's a trivial answer. The amount of energy in the universe is constant according to the law of conservation of energy. It doesn't change. So the rate of change of the energy of the universe is 0. This is our universe. I have two sources of energy in the universe. I have the energy of the surroundings and I have the energy of the system. So then I write du of the surroundings plus du of the system. That is the universe. So what we find from this relationship then is that, or vice versa, any energy gained by the surroundings is lost by the system, and alternatively, negative dus. And I drop these surroundings. I just have the S there. It's the same thing. Just move the equation to the other side. There's always a long debate about, do we call work positive work or negative work? I don't really care what you call it. Just as long as you draw a drawing, in whichever arrow direction you point it, this way is positive heat, this way is negative heat. But depending on the system, right, if you have like a heat exchanger system, two heat exchangers, right, you have to draw a direction for the Q. So one positive Q is always going to be one negative Q. So there's no way you can ever adhere to a single convention. The easiest way to do it is if you have an arrow going in, it's positive. If you have an arrow going out, it's negative. If you draw your arrows wrong, then your Q is just negative. It's not a big deal. Right, so don't fret about the convention of what's positive and negative work. Anytime I ask it on an exam, I'll always say into the system or out of the system. Okay, so now what we're going to do is we're going to just use the definition of temperature. So 1 over T is defined as how the entropy changes of the system as I change the energy of the system while the volume is being held constant. So that's effectively what we have right here. Right? The volume is constant, so how does the energy change versus that? So I'll write out ds of the system will be and ds of the surroundings will be just minus of this. So here we're relying on the definition of temperature to actually tell us what's going on. We'll bring in the second law, which simply states that ds is greater than or equal to 0. One thing that I forgot to mention is that entropy is extensive. What does that mean? What does extensive mean? It's in contrast to intensive. So what's an intensive property?
And it does not depend on mass or
Intensive does not have any function as the mass or the size of the system. So what is an intensive property?
Specific volume.
Specific volume is intensive.
density.
Heat capacity.
Density, what are some of the obvious ones?
Heat capacity.
That is intensive.
Pressure.
Temperature and pressure. Those are the ones that I was kind of go for. So entropy is extensive. So if I have two systems, entropy 1, entropy 2, the total entropy of the systems, I add them together. So the total entropy of the universe then is going to be ds of 1 plus ds of the surroundings, which has to be greater than or equal to 0. If I substitute in my values up here, ds of 1 minus q dot over t is greater than or equal to 0. ds is greater than or equal to q dot over t, or we could write ds is equal to q dot over t plus s gen, noting that s gen has to be greater than or equal to 0. So the sad thing is that this formula right here is, again, sort of this backwards cyclic logic where in order to write out the second law, we have to already have an understanding and concept of the temperature. So then if we were to go to, again, like what we did for the first law, what you typically see in a thermodynamics textbook, ds dt, summation try to string k like the same convention. And this is what we would typically see as the classical form of the second law of thermodynamics that we would start off with in a particular textbook, where you're contributing entropy to the system by the nature of material flowing into the system. You can be adding entropy to the system in the form of heat transfer. And the key thing that's tricky about entropy is when you do transfer heat, it's almost like it's encoded, right? The higher the temperature you have, the less entropy you're giving to the system. And that's why when you have a temperature difference, one system is losing entropy at a lower rate as which the other system is gaining entropy. So when you divide by the temperature here, the differences in the temperature correlate to the differences in how much entropy is being transferred. And that's how one system can only lose a little bit of entropy, the other system can gain a lot of entropy, and that's how you have entropy generation. So that's the tricky part about entropy. Now this always trips people up. Is it the temperature of the system? Is it the temperature of the surroundings? In general, you'll never use this. This is very, very infrequently a useful term to keep track of. In general, what you would do instead is you would integrate this from state 1 to state 2. You have entropy of 2 minus entropy of 1. And then you use this information to solve all your problems. Very, very, very rarely will you ever use this term in your calculations. But it is almost always what people try and solve on homeworks and exams. More often than not, you focus on these terms here. Calculating the entropy as opposed to calculating the Q dot over the T. There's only very specific circumstances where this is something that's easy to solve. So if you have, going back to this example of a heat exchanger, oops. If I have heat being transferred by this heat exchanger, right, this starts T1 hot, T1 cold, T2 cold, T2 hot. In a real process, this temperature is changing throughout the process. This temperature is changing and this temperature is changing. So in order to apply this relationship here, you would more or less have to take a volume element of fluid, follow it through this pipe, integrate it over that particular weird path that it's taking as temperature is changing. Do the same thing with this one over here and then relate the two together. Not a really trivial process. So in general, then what you do is you just say, I'll draw a box around the whole process. Who cares what goes on the inside? And I'll just keep track of entropy 1, entropy 2, entropy 3, entropy 4. That's really how we do it. But this is always the point of confusion, is this term right here. But almost, you will very, very, very rarely see that. The only time this is going to be simple is when you have basically an infinite reservoir whose temperature isn't changing connected to another infinite reservoir whose temperature isn't changing, and then you can calculate the differential rate of entropy generation between the two. So this is useful for derivations and such, but in practice, you don't really ever kind of use it. Okay. So now let's go through and talk about Clauses and Kelvin's systems and convince ourselves that those are valid statements of possible and not possible processes. So let's look at Clausius's device. So in Clausius's system, we have a hot reservoir, we have a cold reservoir, we have some sort of a system, right? And the goal of which is we want to break the second law of thermodynamics. So kind of like what is it? Is that alchemy where you're trying to make gold? So imagine that you're a thermodynamicist in the 19th century trying to generate infinite energy by making a perpetual motion machine. So if you could transfer energy from cold things to hot things, from cold things to hot things, then you could basically generate infinite energy. So your goal then is you've got heat going from the cold reservoir to your magical device. That's what this circle is here. It's the device that you're making. In the case of a heat engine, this could be the engine of a car. And you have heat coming from the hot reservoir. So, is it possible? Can we transfer heat from the cold to the hot system? So, right now, this is the system. So I'm going to draw a little dashed line around our system. Let's write out the energy balance for the system. du is equal to what? All right, we're being accountants here. So we're just keeping track of all of the energy in and all the energy out. So walk me through it. What is the rate of change of the total energy contained within this system here? QC plus QH. And to simplify this, we are going to say it is 0, treating this as an operating in steady state. Right? This is some magical device that can continuously take heat from cold and deposit it into hot. So in this case, in order for this energy balance to be appropriate, QC has to be equal to minus QH, which makes pretty good sense, right? 2 arrows in, one of them has to be negative. So I had to have drawn one of the arrows wrong. Okay, so this is an energy balance. Now let's do the entropy balance. ds, again, we'll also say it's steady state. ds is equal to 0. I'll jump down here. It'll be greater than or equal to 0. ds, we're going to keep track of all of the different ways that entropy is entering and exiting this system. So we'll use this relationship here. So what is my ds equal to? So let's go through one by one. Do I have any flow rate streams coming in?
No.
No.
Do I have these? Did I have heat transferred to the system?
Yeah.
Yes.
Okay, so I have QC divided by TC. This is how entropy is being transferred to the system from the cold reservoir. Plus QH over TH. This is how entropy is being transferred from the hot reservoir. And this has to be greater than or equal to 0 by the second law of thermodynamics. Okay. I'm going to use my energy balance. I'm going to substitute it into my entropy balance. ds is equal to q dot c over t c minus q dot c over t h greater than or equal to 0. I'll pull out qc 1 over tc over t 0. That term goes away. We don't care about it anymore. And then if we rearrange this relationship, we find that according to the second law of thermodynamics, right, 1 over Tc has to be greater than or equal to 1 over Th. We rewrite that by cross multiplying. Th has to be greater than or equal to Tc. So unfortunately, we cannot transfer heat from cold to hot, according to the second law. The other way we could have written this, if we could have included the S-gen term here, so if we would have added plus S-gen, we would have found that it had to be greater than or equal to 0. So you can work through the math the same way. All right. Now let's do the Kelvin system. So the Kelvin and Planck definition of the second law is we have a hot reservoir. We have some magical engine, some magical device that you're trying to create and sell. Heat is being transferred to this device, and work is coming out. Effectively, this means you have a 100% efficient engine. Who wouldn't want that? Can we prove that this is bust? Right? Our system is this cycle. We're going to say it's going to operate under steady state. So we're going to write out our energy balance. It's steady state is equal to 0. What are the things coming in and out of the system that we're trying to keep track of?
Heat and work.
Heat and work. So I'm going to write plus Q and, all right. Oops. W. Okay. So according to the energy balance, this is A-okay. I have not violated the law of conservation of energy in this formulation of this engine. Now let's do our S balance. All right, E balance, just as a reminder of what we did. Now I'm going to write out my entropy balance. And this is one of the major keys to this class. Every exam problem that you get, especially for exam 1, if it's a process, if you write out the energy balance and you write out the entropy balance, you will get a very large fraction of the points on that question. But I promise, a large portion of the class will not do that. So, you get a process, you write out the energy balance. You get a process, you write out the entropy balance. That is always the starting point for a process. When it comes to phase equilibria, the expression you want to write out is the fugacity of phase 1 is equal to the fugacity of phase 2, or the Gibbs free energy of phase 1 is equal to the Gibbs free energy of phase 2. That's the starting point for all of the work that we're going to be doing. So burn that into your brains. Start off with the entropy balance and the energy balance, and it will work out. Okay. The second law of thermodynamics, we have ds is greater than or equal to 0 is what we're going to use as our starting point. Excuse me. In this system here, I only have one method of how entropy is getting into the system. So the ds of my cycle is just going to be equal to the rate of heat transferred in based on the temperature of the reservoir. I'm get rid of that h to make it simple. Greater than or equal to 0. Now for this one here, what we'll do is we'll write it out a slightly different way. We'll say that ds is equal to q over t plus s gen is equal to 0. So if we write it out like this, s dot gen would be equal to minus q over t, which is not possible. It is, however, possible to do the opposite. If I drew this arrow the other way, I would get s gen is equal to q over t. So I can very conveniently transfer work directly into heat. There's no limit to how much work I can waste and convert into heat. But I cannot take heat and directly convert it into work. The only other possibility is if I have a negative temperature, which is not possible, and proving that it's not possible is actually another topic for another day. So the Kelvin and Planck definition does not pass muster with the second law. So in this case here, this is not possible. We cannot have a process that 100% converts heat into work. Okay, I had one more example to go through, but I think we're unfortunately out of time. We'll do it on Friday, deriving the Carnot cycle. Basically, same approach. I think it's just a nice, convenient way to introduce everyone, or reintroduce everyone rather, to energy and entropy balances. But the whole point of starting off here is to slowly build up and convince everyone that thermo is not, it's not as tricky as you remember, as long as we're very meticulous. We start from the ground up and we slowly build the complexity. Well, slowly we'll be very rapidly building the complexity. It'll pick up the pace a little bit next week, quite a bit. All right, see you guys on Friday.